good evening. This is Sai again from NPTEL for TA for your transport phenomena for biological systems. Today I'm little bit under the weather, so you're going to have a explanation in this voice only. So I hope I don't sound like Darth Vader. So, alright then, let's start. Actually, today we have a lot of ground to cover, so we'll give just 5 minutes for people to assemble. After that, we'll start, okay? Alright then, let's start. So, Today we are going to look at a specific problem, and why we are going to look at this specific problem is it has a fair bit of detail inside it, and a fair bit of application oriented phenomena inside it. So this was taken. This is taken from the NPTEL course. So I would give you a minute, and I'll read the problem. The algal broth, after passing through the photo section of a bioreactor, significant. So before this, I'll to understand the background of this problem, please look at the lecture of Dr. G.K. sir and come back here. He has explained it very nicely. So basically, we are going to look at the heat exchanger between a double pipe in a double, I mean, a heat exchange between the hot algal broth and the cold liquid, and we are going to look at the various factors that affect this heat exchange. So the algal broth, after passing through the photo section of a bioreactor, significantly increases in temperature due to heating by the sun. It needs to be cooled before it passes through the photo section again to prevent cell death. A heat exchanger can be used to cool the broth. The broth flows through the inner pipe of a double pipe heat exchanger and is cooled with water flowing in the jacket. The inner pipe is made up of 25 mm Schedule 40 steel pipe. So what is Schedule 40 steel pipe? It's a steel pipe of a given specification. So you need to have a handbook to understand what is this, and then you apply it later. But let's first understand how the problem is solved. The thermal conductivity of steel is 45 watts per meter per Celsius. Under the given condition, the heat transfer coefficients are this and this. All right. The broth, the hot broth, and the cold water. What is the overall heat transfer coefficient based on the outside area of the inner pipe? So basically, what they are asking is inside the pipe where the algal broth flows, what is the overall heat transfer coefficient based on the outside area, that is the outside wall area of the inner pipe. What is the rate of energy removed from the broth? The broth at entry is 40 degrees Celsius and cooling water is available at 20 degrees Celsius. So basically this is very simple, right? We have a fluid that is flowing at 40 degrees Celsius and we have another fluid that is flowing in close proximity at 20 degrees Celsius. The only logical thing that can happen is the transfer of heat from that 40 degrees Celsius fluid to the 20 degrees Celsius fluid. It's as simple as that, right? So yeah, that's exactly what they are asking. Now let's to solve this problem, we need to look at the various aspects of heat exchange and then finally come to a overall conclusion, and from that overarching conclusion we solve the problem. Let me go and check if there is somebody here. No, I don't think so. All right, so a double pipe heat exchanger can be operated in two modes. One is the co-current mode, where the direction of the hot and cold fluid are the same, and the counter current or the anti-parallel mode, where the direction of the hot and cold fluids are opposite. So when it is co-current, this is the THA. This is the cold. This is the distance from the cold fluid inlet, the x-axis, and the y-axis is the temperature. This is the temperature of the fluid at the start, the temperature of the cold broth at the start of the. Uh, this is the temperature of the cold broth at the start of the co-current heat exchange at the inlet of the pipe, and this is the temperature of the hot broth at the corresponding to the inlet starting point of the cold fluid. So what happens is that when there is a co-current flow, there is a heat exchange, and basically the delta T1, or the difference in the temperature between the hot fluid and the cold fluid, as a function of the distance from the cold fluid inlet, decreases because heat exchange occurs. So this is for co-current. So for the um, anti-parallel flow, where where the hot and the cold fluid run in reverse to each other in terms of directions. This is the temperature of the this is the temperature of the hot fluid. This is the temperature at the start of the inlet, the distance from the inlet. So this gets reversed, right? Because it is flowing at the opposite direction. Correct. So see, if you see now, the hot fluid temperature goes down and the cold fluid temperature goes up. See, from hot flow from this to this and from this to this. It's just logic. And what is the ideal scenario here? What is the ideal scenario? The ideal scenario, what is the, let me put it this way, thermodynamically ideal scenario. What is it? Okay, no one has joined. Sorry. So the thermodynamic ideal scenario is simple, right? I mean, the temperature, that's complete heat transfer between the hot fluid and the cold fluid, but that's not possible. However, it is much more efficient in counter current anti-parallel mode. Why that is the case? Go listen to the lecture. Now we are going to look at a set of equations and a set of figures to understand this whole problem. Now we have chosen counter current. So basically Q is the heat transfer rate, H is the heat transfer coefficient, A is the area and, through which the heat transfer coefficient occurs, delta T is the difference in the temperatures. Now the what this means is that, the higher the temperature, the higher is the uh, heat transfer. However, we need to look at it in a much more subtle way. So let's consider the flow in the tubes with the heat being transferred through the surface. So this is the this is the heated surface, and this is the temperature of the wall, and wall temperature, and this is the bulk temperature. So as you know, the wall temperature is always going to be different from the bulk temperature, right? Because there is going to be so that's how heat transfer occurs. It occurs upon layers to layer. This can be correlated, or a simile can be can be attributed to the shear stress, where the rate of change of uh, shear with respect to the distance is zero at the walls, right? I mean, so it's something like that. There is TW2 and TB2, and there is going to be a heat transfer in this direction. I mean, depending upon where the hot and the cold fluids are. It's just a representative diagram. So there are three conventional definitions of heat transfer coefficients. One is so if we take this area, which is a basically since it's a cylinder, it's pi dl. So, and then H1 is the heat transfer coefficient. And so we are talking about, uh, this side, one side of the inlet, TW1 minus TB1. So H is based on the initial temperature difference. So H is based on the initial temperature difference. However, that may not be the right way to look at it, because heat transfer occurs across this section of the tube, and there are two other definitions for heat transfer. And one is based on the arithmetic mean of the wall temperature difference, the wall temperature and the bulk temperature, TW1 minus TB1 plus TW2 minus TB2 divided by 2. And HA is based on the arithmetics. HA is the arithmetic mean of the temperature difference, based on the arithmetic mean of the temperature difference. And there is a log HA. This can also be written in terms of the logarithmic mean of the temperature difference. This is the case. For more detailed understanding of these three equations, please look at the lecture. Now, let us go to a section of the wall. So we know that the temperature. There is a temperature variation if the inside wall temperature is unknown, or if the fluid properties change appreciably along the pipe, which is the case. And then it becomes difficult to predict the heat transfer coefficient. So basically what we are going to do, we are going to go to our friend calculus, and what we are going to do is we are going to take an infinite semi-L piece of the pipe with a thickness dz, and we are going to rewrite this equation in terms of this. So basically dq dot equal to h local into pi d dz into tw minus tb. So that is one part. Okay. Now we have looked at the heat transfer, from the heated surface to the cold surface. Now let us understand the heat exchanger. Let's consider the heat exchanger itself. I hope you guys understood this point, because if you don't understand, it's going to be a problem from now. So let me just. So basically, this is one part of the one side of the wall. This is the other side of the wall. So we can either take the temperature difference on either side of the wall, or the arithmetic mean of the both sides of the wall, or the logarithmic mean of the both sides of the wall, which corresponds to these respective equations. Alright. Okay. Let's just pause here for a minute so that you digest what all has been said till now. And yeah, we are pausing up to here. I would suggest you just, I'll slowly go down. No, I think this is fairly easy to understand. I'll slowly go down from this so that you'll be able to understand. Anybody home? No. Now, let us consider the heat exchanger itself. Let's consider the heat transfer across the heat exchanger inner pipe wall. So basically, this is the warm fluid, this is the cold fluid, this is the inner pipe wall. Every wall has a wall thickness, right? So the overall, so basically the warm fluid is at a temperature TH, and at this point where conduction occurs between the thickness of the wall, the wall temperature is TWH, and then the cold fluids temperature is also something like this, is basically TC and TWC respectively. So what you can see from this, you know, how can we describe this phenomena? Let's leave this thickness part out. If you want to describe this phenomena where there's a gradual decrease followed by a sudden decrease, how will you decrease? I mean, how will you model this curve? Simple, right? It can be described. It looks like the Michaelis-Menten kinetics number one. It looks like an exponential decline or a parabolic decline, as the case may be. So that's how we should think about it. So basically, the equations that will be derived will be based upon these factors. If it's going to be linear, it's going to be a different equation. If it's going to be exponential or parabolic, it's going to be a different equation. So here it is linear. So we are going to divide this whole problem, this whole heat transfer from the warm fluid to the outer wall, and from the outer wall to the inner wall, and from the inner wall into the bulk fluid of the cold fluid. Okay, so the overall resistance to heat transfer is these three heat transfers are in series, right? So basically they add up: resistance of warm fluid plus resistance of the wall plus the resistance of the cold fluid. So now, based on this figure, how we will be deriving this for the inner fluid, the warm fluid, this one, the rate of change of heat transfer with respect to the area, the local area of uh, we can say this area. It's basically Hi into Th minus Twh, where Hi is the individual heat transfer coefficient for the inner fluid, the warm fluid, the algal broth. So at the wall, this conduction occurs, correct? So conduction, how do you write conduction? Is basically Fourier's. Yeah, I think it's Fourier's relationship. So dq by dAw, where the Aw is the area of the wall, is equal to minus dt by dy at W, given the wall thickness. Now for the outer case, in this case the cold fluid, similarly like this, we put like this. However, the TWH will come this side and TH will come that side. Why? Because of the fact that uh, it's simple, right? Here this is hotter than this. We need a positive answer, so we put it like this. Now delta T equal to TH minus TC. Basically, the delta T that we have here, this is also delta T, this is also delta T, this is also delta T, based upon which equation that we use. Uh, this delta T equal to TH minus TC, right? And Basically you just substitute this, right? Th minus TWH plus TWH minus TWC plus TWC minus TC, everything gets cancelled. So basically LHS equal to RHS. Now we are going to use the RHS now in some time. Okay, now let's consider the conduction across the cylinders. So now we looked at the conduction we looked at here, this one, these two are not conduction, this one is the conduction, right? So we are going to look at this. So how do you look at this? We derive a shell balance. So basically this is the inner radius of the pipe where the hot broth flows, and this is the outer diameter of the pipe, or the radius diameter. This is the inner radius, this is the outer radius respectively, and this is the temperature of the outer fluid. The temperature of the inner fluid will be Ti correspondingly. So basically we have Q equal to minus Ka into dt by dr, and or equal to minus K into 2 pi RL into dt by dr. Now we just have to this is also a type of Fourier's equation. Yeah, if I remember it right, yes it is. But this is how the equation is derived. So so what we need to do is we need to rearrange it and then integrate it. When we rearrange it and integrate it, this is what we get. Q dot. What is Q dot? Q dot is the rate of heat transfer, or heat transfer rate, whatever. Q dot equal to K into 2 pi L into Ti minus T naught by ln of R naught minus Ri. So basically if you integrated this, you will get this. It's very simple. It's a simple integral. I'm not going to explain it. You can just put it in. You can just put a pen and paper, and then you can do it. Okay. So let me give you a break here. So understand the shell balance again. So basically, this is the inner radius. This is the outer. This is the inner radius. This is the outer radius. So basically, this is the temperature of the outer wall, and there is a temperature gradient, and heat transfer occurs. And now, how do you formulate into this equation? Using this equation, as I said before, and then once we integrate it, we get this. So see, we first saw up to this, we took an infinite semi-L piece, and then we looked at the heat exchanger. And now we are going to look more. I'm just going to give you a second or a minute to digest all this. Just look at the shell balance for some time properly. Alright, let's move on. So basically when you integrate this, you will get this. Now what we are going to do is, we are going to change this uh, into the logarithmic mean area. So why do we do that? You go look at the lecture. The answer lies somewhere here. You look at the lecture, you'll get it. So AL hat, so basically Q equal to K into AL hat into Ti minus T naught by R naught minus Ri, where AL hat equal to 2 pi L into R naught minus Ri by ln of R naught by Ri. So basically is equal to so R naught by Ri by ln of R naught by R naught minus Ri by ln of R naught by Ri is basically the R hat, right? So that's the logarithmic mean radius. So using the above, at the heat exchanger wall, we can write the rate of conduction is with respect to the area of with respect to the areal thickness is dq dot by dal hat equal to k into twh minus twc divided by xw. Now, if you see this al hat, if you just rearrange this al hat, there will be some here. There will be some terms which will be cancelled, some terms will go this side and this that side and stuff like that, and we'll get this. So if you want to do it, as I said before, take a pen, paper, and do it. So so this is the rate of heat exchange at the heat exchanger wall. dq dot by dal hat equal to k into twh minus twc by xw. What is twh? This is twh. This is twc by xw. Thickness of the wall. Now we substitute equation this equation in equation 9. In this equation, as I said, I told you it will come in handy, right? So basically, uh, when we substitute this, I'm not going to go into what happens when we substitute it. It's clearly mentioned in the lecture, so you can go look at it. So I'll just going to read out the formula, but before doing that, let me go and show you this once again. So basically, delta T equal to Th minus Tc equal to the rate of heat transfer by the hot liquid to the interface, and the conduction across the areal thickness of the wall, and this is the rate of heat transfer at the the outer pipe, which is the cold fluid. So what we are going to do is, we are going to just substitute this equation in this equation, and what we get is delta Th minus delta Tc, when the Th minus Tc or delta T equal to dq dot by dai hi plus dq al hat into xw by k plus dq dot a naught h naught. So this is the outer radius, outer section of the inlet pipe. So basically dq by dA naught, that's what we want, right? So we rearrange it, we get this Th minus Tc divided by dA naught by dAi into 1 by hi plus xw by k into dA naught by dAl hat plus 1 by h naught. I understand I'm just simply reading these things out, but this is the only way to go about this. We have to go about this step by step, lest we miss something. So we know that dA naught by dAi equal to d naught by di. So basically, what is dA naught? Is basically it's 2 pi area is 2 pi d, right? So basically it's 2 and pi are going to be same, so basically it's going to be d naught by di, and dA naught by dAl hat equal to d naught by dl hat. So dl hat is the logarithmic mean diameter. So dq by dA naught equal to, if you substitute this, it's going to be dh minus dc divided by d naught by di into 1 by hi plus xw by k into d naught by dl plus 1 by h naught. So we got this. So coming to the flux, where flux is the driving force by resistance, or 1 by driving force into resistance, sorry, 1 by resistance is the driving force, where 1 by resistance is the conductance. So the conductance U naught equal to, we know this one, right? So U naught is the overall heat transfer coefficient based on the outer area. So we are just changing this, right? So delta T is not no delta T gets cancelled, and we get this equation 1 by d naught by di into 1 by hi plus d naught by dl hat into xw by k plus 1 by h naught, where u naught is the overall heat transfer coefficient based on the outer area. Similarly, based on the inner area, we can derive the same. So basically here we put A naught H naught, right? We need to put AI HI, and then we can derive it. So how do we derive it, and stuff like that? You guys use this as a template and do it. You will get it easily. And after this, it's now basically a matter of taking the standard tables, looking at the various values in the standard tables, and substituting them, and then coming to the answers. I will leave that for you guys to figure out by looking at the lecture. But yeah, this is quite, I mean, on the face of it, this looks complex, right? But if you divide it, like how Dr. G.K. sir has divided it, in terms of the first the outer, the outer tube, then the heat exchanger itself, how the conduction and convection, not convection, heat transfer occurs. And then using a shell balance, and then coming at it. So basically, if you these looks like very giddy formulas, right? But if you start from the first principles, you can easily arrive at this. It's not a big deal. As I said in one of my previous lectures, a complex phenomena is a set of simple phenomena that needs to be solved parallelly and / or concurrently. So I will leave you to that. So if you have any questions, I will be happy to answer, but I don't think anyone is here. So if you have any questions after seeing this lecture and want to know how to proceed forward, I would suggest you to look at the two lectures of Dr. G.K. sir in both the lectures. It's two parts, in fact 3 parts, and then you will be able to appreciate the simplicity of this complex phenomena. So that's about that for today. I don't have anything else to share with you. If the class is filled with people, I would, since I think this is the last session of our NPTEL TA. I hope someone comes and joins us, if not to ask questions, just to get to know about ourselves, perhaps as a parting shot. So I'm going to wait for the next 15 minutes, yeah, for that to happen. Ah, today is a tough day, guys. I don't know. I have some. I'm very tired today. Looks like I'm having fever. I don't know what is the problem. The good thing is I've not lost my sense of taste, so I don't think if anybody is thinking that if you join this lecture you may get COVID or something like that. I can assure you that this is not COVID. It's just some basic tiredness. I've not lost my sense of taste or smell. So this happened. I'm not joking. During the height of one of the during the height of one of the COVID peaks, there was a postdoc who wanted to have an online class with a professor. The professor will go unnamed. The postdoc will go unnamed. And so when the postdoc initiated the conversation, the first thing that the professor noticed was that where are your where is your mask? He was in his house actually, and she was in her house, and they were interacting through video call like how we are doing right now. And she asked where is the mask. So he said he was flabbergasted. He didn't know what to say. So he said I don't have it. And she said that put on a mask and come, then only we'll have the lecture. And then they say, and then she switched off the video call. That was hilarious. I hope people are there. People would have been here to listen to this story as well as all my previous lectures, but that's okay. Actually, okay, that's fine. I mean, if you can do it on your own, who am I to stop you? I wish you well for your exams. And yeah, we'll wait for some more time. Class has not ended. it then. I mean, we'll wait for a minute, and if nobody joins, we are going to end the class. So, I hope whatever you have learned till now comes in good stead. I hope I wish you well for the exam. All the best, and yeah, see you guys. Bye bye.